Hello. So today we're going to be talking about measuring runtime and performance analysis. And we've got a demo ready. I'm going to open up the bash shell in a little bit and do an example. First of all, we've got this same function that we introduced like a couple lectures ago, where we mentioned doing the product of everything but the current element to get the different values. And this is the slightly simpler version that has two separate loops instead of nested loops. However, this one, I'm sure you've gone over with Professor Darden, had a problem with zero values inside of the input. But if there's no zeros, we get the right value. It does it really quickly. And if we wanted to, we could add a few variables to this. It would still be O of n, but we could get it to avoid the problems with zeros inside of it. Now, when we look at measuring complexity, we've talked about in the last couple lectures of doing it analytically, looking at the code or pseudocode, creating some type of recurrence relationship, solving it, finding out what the complexity is. And we can do this with code, we can do it with an algorithm, and it's very good at making predictions, especially before we code. So we can do this on our design of the algorithm before we code it and see if it's going to meet our needs. We might also do an empirical analysis, meaning using data. And we have to have a program for that because there's no pseudocode compilers. So we have to have real code, we have to have some input, and then we can use a host of different tools to measure how long it takes to run that code. And we're going to look at a couple different tools to use today. We can also test it on a variety of sizes of inputs to see if we have the sort of behavior that our analysis, our theoretical analysis, predicted. Now, when we say programmatically, one thing we can do is we can put code into the program itself to measure how long it's taking. And how we do this can vary depending on what language we're using. Even in just C and C++, there's a couple different ways to do it. So we have an example here coming up that Camille wrote in C++ using something that's already built in called chrono and standard chrono. So using those, you don't have to understand every line of this, but the basic idea is there are some tools in a library that we can use, and there's a small class here which has a few simple things. It's got some member variables, it's got a constructor, it's got a start the timer and a stop the timer. So you can say start and stop the timer, and then you can say, I would tend to look at the last one first. Tell me how long that took as a double. How many seconds did that take? And then if I'm going to reuse the timer and I want to time this thing, print it out, and then time something different and print that out, we could reset them in between those two different parts. And we've got over in the left pane, we've got in the right pane, we've got a little example program there that says, create me this timer, and then I would like to start the timer, do some stuff, stop the timer, and print it out. So this could be, say, project one. We could say, hey, let's time how long it takes to read the input. And one thing you could do if you're doing this with project one is don't send it to cout, send it to cerr. The autograder does not grade cerr. And so if we send something to cerr, the autograder will record it and it'll save it, but it won't use it for correctness testing. And so if we send it to cerr and we forget to take it out before we submit to the autograder, it won't make us get a 0 for every test case because there's this time in seconds that wasn't asked for. So the other caveat is, if you were to do this and submit to the autograder, make sure that cerr isn't inside of a loop. Because If I start and stop a timer and print and output a constant number of times, it's not a big deal. But if we do it a large number of times, and there's a little inset box up here, if we do it a large number of times, then it might take extra time. Think about if we were taking an exam and I kept looking up at the clock. Oh, there's 97 minutes remaining. Oh, there's 96 minutes remaining. 95 minutes. Still 95 minutes. And if I spend all my time looking at the clock, I spend less time working. So that's the thing, is if we did do this on our project and we submit it to the autograder, we want to make sure that we're not doing this stuff inside of a loop. So we time task 1, say reading input, print out the time, reset the timer, and then we do stuff 2, which could be like doing the search. And then we print out the time. And if we wanted to, we could then reset the timer, start the timer, produce the output step, stop the timer, and print how long it took to do the output. So we could do that if we wanted to inside of our program by including the file that has this code in it and starting and stopping the timer a few times. Now, that requires us to modify the program, though. What could we do if we don't want to modify the program? Well, we've got I'm out of order here. So I've got an example almost ready to go using the code that's here. And it says, so there's a link there from a browser. You can grab the file directly, or from a terminal, there's a wget command. So that's what we're going to do over here. Let me get my switch over to my shell, and there we go. Okay, so I've got this prepped. Like I'm in a folder that's got nothing in it, but I'm going to teach you a command that's really useful in Unix. Exclamation point, which programmers many times will refer to as bang because it's a lot less syllables and faster to say than exclamation point. So the bang, if I do bang, let's say WG, what that says is I want you to rerun the last command that started with that sequence of letters. So bang WG says go run that wget command, and you can see here I type bang WG. On the following line, it shows me what command it found. And then here's all the output of basically connecting to that link and downloading the file. And here we go. We know it's right when we got saved 3831 should be probably the number of bytes in the file. Yep, there we go. Okay, so we've got the file, and I also prepped, if you look at the next slide in the slides, there's a G++ command, because I didn't want to take the time to grab a make file and change the target and stuff like that. So just bang G, go get me the last command that started with the letter G is G++. And notice I wanted to make sure I ran this. I need C++1Z or C++11 to make sure that like the C++ stuff is done correctly. And -03, optimization level 3. This says optimize for speed. All the standard speed ups, turn them on. So now, if we look at our folder, I've got an executable called search. So let's run it, .search, and it'll tell us, oh, what do we got to do? You must specify B or L for the type of search. Sounds like binary or linear. And the number of items. Okay, let's do a .search. Let's do a linear search of, let's say, 1,000,000 items. Okay, so it says filling the vector took 0.003 seconds, and then it found 59 out of 100 items. So what it did was it filled a vector with 1,000,000 items, then it did 100 searches, and basically it found them a little over half the time, and that searching took 0.075 seconds. All right, let's increase it. All right, let's go up to 10 million. So, that's another thing. If you don't know that one, I hope you know that one. Up arrow. Up arrow goes to the previous command, and I can just edit it by adding a 0. Okay, took about 10 times as long to fill the vector. That makes sense. Took more than 10 times as long. Like we would have expected like 0.7 seconds, but it took like almost 50 times longer. Well, still, it's a factor of 10 times longer. All right. I can tell right now if I move up to another, from 10 million to 100 million, we're going to be going like 35 seconds at least. I don't want to wait that long. Let's try binary searches. So /search, oops, there we go. And that's another one. If you hit tab, like I type ./se, hit tab, it'll complete it for you. I just do these things without thinking sometimes. Okay, let's do a binary search. 1, 2, 3, 4, 5, 6. So there's 1,000,000. Okay, took about the same amount of time, 0.003 seconds to fill it, and took about half the time to do the searching. Half the time to do searching. Well, let's move up to 10 million. Took about the same amount of time. Okay, that doesn't seem right, right? It shouldn't take about as long to do binary searches as it does to do linear searches of 10 million items. So there's got to be something going on with this code. So let's fire up our editor and search. And here I hit tab. It goes bing bong to tell me there's more than one thing. If you hit tab twice in a row, it'll show you a list of matching files. So then if I type dot and hit tab again, it'll complete the one with the extension. All right, so let's edit that file and let's look at it. Okay, in-class starter code for lecture 3. Oh wait, we reordered lectures since then. I guess I should go edit this file. So lecture 4 now, we reordered our lecture slightly. And then here's Amir's code, and that's all fine. We copied that directly from him, and we just threw it in here rather than having 2 separate files and 2 wget commands. We just put them all in one file. Okay, so here, perform a straightforward linear search through the input vector for the given value. Should theoretically have O of n complexity. Note this code contains an intentional bug we'll discuss. Okay, well, linear search took a little too long. What about binary search? Okay, aha, here we go. Performs a binary search through the input vector looking for the given value, assumes it's sorted order, and should theoretically have O of log n complexity. And this one contains an intentional error also. All right, so let's scroll where we can see the whole thing. All right, so it says you give me a vector and a value to search for. I will figure out the inclusive lower bound and the inclusive upper bound. So where should I search between? So I should search between low and high. So while high is greater than low, so while there's still places to look, find the midpoint, get the value. So I just copied the value there so I can refer to it. If that middle value is the one we're looking for, we return the middle index. Mid is an index here. So return that middle index, else if it's less, then move the high end to be mid minus 1. So move into the first half, else move into the second half. It sure sounds like a binary search. We found it, but it's not the right complexity. It should theoretically be O of log m, but it looked more like n. The problem is not in the function, and it returns -1 if it didn't find it. The problem is not in the function. The problem is in the line of the function. It says, you give me a vector by value. Oh my gosh, okay. If we pass a vector by value, it takes O of n time to copy the vector before we even get to the binary searching. So let's change this to a reference. So let's just put reference in here, insert an ampersand. Let's go up and see if there's the same problem in linear search. Yep. So we'll just, here's a command in VI, dot redoes the last command. So I'll insert an ampersand there. So then I'll write this out and let's go back and we'll recompile it. Bang G to get me back my G++ command. And it says binding standard const vector to a reference discards qualifiers. This is one of those compiler error message written by people who can write compilers but can't talk to human beings. What it's saying is basically we tried to modify a vector that someone else in test search, someone else said, I'm going to accept this vector by const reference, and they gave it to us. Okay, so test search accepted a const reference, and we accepted a reference. Now, here's where you don't want to overreact. What many students say is that, oh, that test search function, we got to go take the const out of there. That's the wrong answer. what we should be doing is adding counts to ours. Because if we're doing a linear search, I don't need to modify the vector to do a linear search. So there's another function that said, hey, if you give me a const reference to a vector, I will test searching it and I will not modify it. Well, we don't want to take out that const, we want to add const to ours. We want to say, hey, let's pass this not by reference, but by const vector reference. And we'll go down and make the same change to the binary search. So because we don't need to modify it, we're going to pass it by const reference. And that follows the rules. If you look at Canvas Files, Resources, Optimization Tips, says basically if you're going to modify something, pass it by reference. If it's a primitive type, or I should say else if it's a built-in type like int, double, bool, any type of integer, pass it by value, else if it's a large object that we don't need to modify, pass it by const reference. So we'll write that out and we'll recompile it, bang G. There we go. So that compiled. Now I don't want to do bang dot because it would go to the most recent one. So let's redo our linear searches now. So here's a linear search of 1,000,000, linear search of 10 million. Oh, look at that. See, that took about 10 times longer. Linear search of 100 million, about 10 times longer to fill it, and a little over 10 times longer to search it. Not too bad. All right, now let's just change that million. Let's do a million binary. So million binary, the searching took so little time that we had to go to scientific notation to see that number. Okay, 10 million, still scientific notation. Took a little bit longer. Look at that. Look at that. We increased the vector size by a factor of 10 and it took about twice as long. All right, let's go to 100 million. Okay, we're actually now down to 0.0000188 seconds. Okay, a billion? This is either going to work or it's going to run out of memory. We'll see. Okay, there we go. Look at that. It took, again, about twice as long to go to double size. Now this one, if we go to, so that's a billion. If we go to 10 billion, we're probably going to seg fault or some sort of error because I don't think they're going to let us grab, segmentation fault. And the fill vector I think isn't accurate because I don't think we got the whole 10 billion elements, which would have been like 40 gigabytes of memory. Okay, so that's the demo we wanted to look at of how we could do it inside of a program. I gotta switch my source back here. Okay, there we go. So then there's a slide here of the stuff we just did, try it with different numbers, and we fix the code. Now, when we look at taking those numbers, if we say threw those into a plotting tool, we could plot those numbers out. And the one thing that these two graphs are showing is that if our input is too small, we might not really see the asymptotic relationship. These 4 points here, 1, 2, 3, 4, are the same points over here. But this one, we said, hey, let's go even larger than that. And we start to see, hey, this is looking maybe like a quadratic curve. So if our input is too small, that's why I skipped straight to 1,000,000, is I knew from having run this before that even a linear search of 1,000 elements wasn't going to show me much. So when we do empirical results, we want to either look at the trend in the numbers or plot it, but we need a big enough N to actually see the trend. Now, when we run this and we get different results, when our prediction is different than our experiment, what if our results are worse than we predicted, just like we had? So our results are exponential when the analysis is linear. Or with binary search here, what if the results looked linear when our analysis says logarithmic? Well, there could be an error in the complexity analysis. We could have made a mistake when we said a binary search is log n. Seems unlikely, that's pretty well known. So then it could be an error in coding. It says check for extra loops, unintended operations, etc. I think the passing by value could be considered either a unintended operation or etc. We did not intend to copy that whole vector, but we did. All right, what if our experimental results are better than what we predicted? So we got, say, a linear when we predicted exponential, or a logarithmic when we predicted linear. Well, one thing that could have happened is we could have not generated enough random numbers to get a really good experiment. Maybe we just happen to get a best case. So that's why we might run it more than once. Or like with this one, where we run it with 1,000,000 elements and generation of random numbers, then we can get, hopefully, if we've got a good random number generator, we'll get a good distribution of random numbers, and we'll get a realistic analysis. And if you look back at the code, here, let me switch over for a second. If we look back at the code, what we did is in here. So here's the test search function. Remember the one that says I'm going to do something with a const vector reference? So what we did is we told it do like 100 searches. So what it did was it created a random device. It created a Mersenne twister, which is a type of random number generator, off of that device. And then it said, I want you to give me a uniform integer distribution from 0 up to, but not including, this is STL sense, 0 inclusive up to 2 times the vector size exclusive. Well, wait a minute, what did the main do? So main said basically push back the even numbers. So it said, like we said 1,000,000, it reserved 1,000,000, and then it ran 1,000,000 times, pushing back, so it pushed back 0, 2, 4, 6, 8, up to 2,000,000. So it pushed basically all of the even numbers from 0 to 2,000,000. So then when we did the searching said, hey, let's pick a number in the range 0 to 2,000,000, inclusive, exclusive, and let's see if it's in there. That's why it should be about 50% of the time. So it generates an odd or an even random number in that range, which only contains even numbers. And then we search for that random value. So we do a binary search, we do a linear search, and we count up how many were found. So this is an example of using random numbers. We say, make me a random device. That basically says, every time I run the program, start at a different set of random numbers, as long as you don't run it twice in the same second. Create a Mersenne twister off of that, and then create a uniform integer distribution off of, or in this range, and then roll me a random number, so roll me a uniform distribution off of that random RNG is random number generator. So get me a value out of this uniform distribution using that random number generator. So this is how you can generate random numbers in a range. Okay, let's go back to the slides. And so how could we use that? You could say, oh my gosh, I'm running out of time on project 1 and I can't find the bugs. Well, you could take the code basically here and use it to generate random numbers. So you could say things like, oh, I'm going to go through my map. I'm going to tell it how big to make the map. It's going to create a 2D vector, and it's going to go through every location, and it's going to roll a random number in the range, let's say, 1 to 10. Right? So if the random number is in the range of, or let's say, so I could do 1 to 10 or 0 to 9 or whatever. Let's say I do it 1 to 10. If the number is 1 or 2, I put a wall there. If it's 3 or 4, I put a letter, a lowercase. 5 or 6, I put an uppercase. And 7, 8, 9, or 10, I don't put anything there. And then when I have to generate a lowercase or uppercase letter, I could generate another random number to generate the letter. And then I would, after I'm done, I would go through and say, roll me a random row and column, put an @ sign there. Roll me a random row and column, put a question mark there, and hopefully they're not the same as the start location. I've got a file. And I could create a program that could generate 15 of those in a few minutes. Once I got the program written, I can generate 15 files. There, go to town, submit 15 files to the autograder. Okay, so back to where we were, which was we may not have gotten to our worst case scenario. So with good random number generation, it'll probably be average case. But if we get results way better than we expect, maybe we just happen to get best case. I could generate 1,000 by 1,000 with 10, 20 colors, and then when I roll up the @ sign and the question mark, they're 2 squares apart, and it solves it really, really super fast. Could happen. Okay, so error in complexity analysis, again, maybe our analysis of the algorithm is off. Error in our analytical measurements, so maybe we didn't start and stop the timer at the right point. Maybe we didn't do a big enough N, so just maybe my empirical analysis just went wrong. I could have a incomplete algorithm implementation. So maybe I did the input and the output but forgot to do the searching. And because there was no solution found, it was easy to print output. Well, if I don't do all of the work, then yeah, my timing should be off. And also the algorithm implemented could be better than the one analyzed. So you could be doing a task of doing some searching and binary searching and stuff. You say, well, I've got to generate random numbers, but then I'm going to sort them, and I'm just going to write a bubble sort. And then when you get to the code, you go, oh, wait a minute, we had that merge sort from last semester. I'm just going to go grab merge sort instead of writing bubble sort. So maybe you just chose a different algorithm at implementation time than you did at design time. So you could have just done something, changed what you were doing, and so you got better results. Okay, what if our experimental data matches our predictions, but it's just running too slow? So one thing is, it could just be that we're just going with too big of an N, right? It could be something like, oh, I'm not using O3. And this isn't too big a deal in like project 1, but when we get to project 4, where we're doing a factorial complexity, I've had people say, oh, Dr. Paley, my code is so slow, it's just like 30 vertices. You said it would take a second, it takes like 10 minutes. I say, are you running that inside of Visual Studio or Xcode? Yeah. That's not an optimized build. That's not O3. That is instead G3. If you're inside of Visual Studio or inside of Xcode, or possibly inside of VS Code, you might be in a debug build, not an optimized build. So if things seem too slow inside of your IDE, maybe just run that to command prompt when you run the make command and make sure you've got an optimized build. So that's a simple mistake to make, is just not to know that Visual Studio and Xcode create debug by default. And there's a way to change that. I know how to change it in Visual Studio. It's just on the bar up at the top, you just change the target, and there's a little drop-down button that says debug. You change it to release. And in Xcode, I think it's somewhere in the scheme. I don't remember Xcode that well. And then also, if you're a little bit too slow, we might just look for improvements to the constant factors. 10n is still n, but 5n is twice as fast. Okay, next section. We could use a profiling tool. So they're talking about this in lab, and here's an example from a larger program from the program in 280 that did some image analysis. And when you run it with perf, you can like open up and see how much time is spent on a function. You can hit enter and it'll open up and show you the things that it called. So that's what the different columns mean. Like there's up here, it's maybe hard to read on screen, children and self. So children means this thing and everything it called. Self means just this thing. So you can see that main really didn't spend that much time itself, but main and its children spent a lot of time. Children meaning all the things it called. And you'll also see some things in here that are like, hey, they're STL stuff, like standard basic thing that I don't care about. But it's nice to know that, like mem copy, part of my time was spent copying memory. Okay, I can't control how long that takes, but maybe I can control how often it happens. Maybe I'm copying stuff too often. Now, there's also things that we can do. We can instead of running a program, we can run a program with time or user bin time. They give equivalent results. So basically, like if I was going to run my program like /puzzle, like -q less than spec.txt, well, spec.txt probably isn't going to take that long to run. How about if I do it with I can't remember the exact file names, but I could do it like less than large.txt. And also another thing I want to do is I want to say greater than like output.txt. If I don't send the output to a file, I might end up timing how long it takes for the output to go scrolling by. With a big file, that could take a while. So I don't want that to be too big a factor in my timing. So instead of just running /puzzle, I could put user bin time or just time in front of it. So this is basically saying, hey, user bin time, do this thing, run my program, redirect the input and output like I say, and tell me how long it took. So on the next slide, we've got an example of running it with a built-in command, built into Unix called dd. dd stands for disk dump. Unix commands don't always make sense. Time, that makes sense, time how long this takes. But dd disk dump basically is saying copy from this input file and write to this output file. What's the input file? Dev is the device folder. So it's a reading from the device 0, which is an infinite source of zeros. It gives you as many zeros as you could possibly want. It says send them to the output file dev null. Dev null is called the bit bucket. You send anything to dev null and it disappears instantly. So this one basically read from an infinite source, wrote to an infinite sync until I killed it with Control-C. And I really do mean Control-C. Even on a Mac, you need to use Control here, not the Command key. So then this is the output of dd telling me what it did. It read some stuff, wrote some stuff, and then this is the output of user bin time with the most important one bolded. So it says 0.26 user, 0.65 system, 0.92 elapsed, 99% of the CPU. So what this is saying is user time is how long this program dd took. System time is how long the operating system spent on your behalf. So that was basically a lot of like 2/3 of the time or so was system time, basically reading and writing. It wasn't your fault that it took that long. And when we do the autograder, we look at user time, not system time. So, but 99% of the CPU, why didn't I use all of the CPU? So here's, like I said, the user system elapsed. The percentage is basically the user plus the system divided by the elapsed. This might be the user time plus the system time might add up to less than the wall clock because you don't get to keep a CPU. Your program feels like it started running and then it finished. But what really happened is every quanta is a unit of measurement. So every quanta, whatever the operating system decides is your time, basically the operating system says to your program, here's a CPU, start running. And then a quanta later, it yanks the CPU away from your program and then maybe gives it to someone else to do something like virus checking or running a browser or whatever. And then at some point, when there's a CPU available, your process gets it back. And your program doesn't know that. But that's why user plus system generally adds up to less than the wall time, is because there's time where your program is not actually running even though world time is passing. So that's what's going on there. And it happens invisibly to your program. Your program can't tell it happened. You might even be given, CPU 0 and then stopped and then restarted on CPU 2. And that's system time spent on your behalf, was moving your job from one CPU to another. So all those things happen without your knowledge. But I hate to give like magic answers of, well, just don't worry about why the total time doesn't match the wall time. I like to tell you why. Not going to be on the exam, but good to know. Okay, another thing we can use, another tool, is Valgrind. And it's supposedly, from what I read online, it's supposed to be pronounced Valgrind, but it sure looks like grind, and it really is a grind sometimes to use it. So I'm going to go with Valgrind. So when we run Valgrind, and it's more important especially to do this with a debug version, let's go back to our window, and we're going to look at using Valgrind. All right, so what I'm going to do is I'm going to bring this program up, and I'm going to put a bug in here somewhere. Now, everything is based on the size of the vector. What if I did I is less than or equal to number of items? G++, /search, B, 1000. Okay, well, it didn't die. Let's see what Valgrind says if I run this. Okay, I didn't. Okay. Oh, okay. Yeah, that's just making a bigger vector. Okay, let's go up and let's add a bug to linear search. That's going to be easy to do. Yeah, let's add a less than or equal to in here. That should kill it. Okay, so when we do a linear search, we're going to go off the end of the vector. Bang G, bang. Oh wait, and I got to rerun this with a linear search. Now it says it worked okay, Valgrind, and so it looks like it found 46 out of 100. Let's run it with Valgrind, even though it looks like it works. Aha! Valgrind says invalid read of size 4. That's almost English. Okay, and it runs in search, and it's at this memory address. The memory address, I don't care about memory addresses. I care about lines of code. Well, the problem is this is a build that was optimized for speed. So let's rerun this with dash instead of -03. Let's compile it with -G3. Right, now let's run it with Valgrind, which, like I said, it looked like it worked, but we know there's a bug in it. Even if you think your code works, run it with Valgrind. So here's the invalid read of size 4. Now, all of this stuff, see, look at the indentation level. One space after the double equals starts a new error, and so there was only one error. Now what we want to do is we want to go down to the bottom of this error and look upwards. This is the call stack. And then there's an invalid read, and then this is another address. This is more about the address error. So there's two errors here. So I can look, I say, hey, main line 138, called test search line 106, called search.cpp line 53. And that was an invalid read. And then there's more details. There's a new call stack here, so main line 128, called into vector line 75. Okay, so let's look at what we want to do is we want to look at line 128, we want to look at line 53 are the two interesting ones, because those are, in each of these call stacks, that's the highest line of code that's recognizably ours. Okay, so let's look at line 128 and line 53. Okay, so line 128, let's turn the line numbers on. Okay, so here's the aha. So what it's saying is this is who reserved the memory. So this line of code here is who allocated the memory, and then line 53 is the one that did something bad. It looked at an index that didn't belong to me. It doesn't necessarily tell you where the error is, but it tells you where the error occurred. If it occurred in this line, really the problem is here that we stepped off the end of the vector. But even though the program ran, even though it looked like it found about 50% of them, it's still good to run a program with Valgrind to see if there's any errors in there. Now let's undo this change. Let's go make another error. What I'm going to do is I'm going to, oh, this won't work. All right, yeah. Okay, let's do a reserve, and then let's say something like this: vector square brackets I is equal to that. So I did a reserve, and then I'm going to put stuff in there. Let's see what Valgrind says about that. Okay, it doesn't see that as an error because it is really my memory. It is memory, I allocated it, etc. So it didn't think that was an error, even though really it is, because the vector size is really 0 at this point. So nobody looks at it. But really, these are invalid sort of accesses. So we could create all kinds of errors in here that would cause problems. So Valgrind is good at finding those for you. So even if you think a program works properly, run it with Valgrind. If you did something like, oh, it says force a leak. Okay, let's go back and let's force a leak and see what happens there. Okay, so to force a leak, let's just undo all these changes. All right, so let's say I did in here, let's say I did exit of 0 instead of return 0. All right, so I exit 0. Let's build it, and let's run it with Valgrind. And it says, so there's nothing that I can definitely say is lost, but there's memory that's still reachable. And that's not good. So it's in, and it says, heap summary says, in uset exit, there's 4,000 bytes in uset exit. And this on the autograder would tell you that you've leaked a memory. You would lose points for this. So we can say, okay, let's run Valgrind. It says, rerun it with leak check full to see details. So we add an option to Valgrind, not to our program. I'm just going to copy that and paste it, put space in there. Okay, so leak check full. Let's rerun that. It says, oh, this is reachable. Those to which a pointer was found are not shown. Rerun it with leak check full and show leak kinds equals all. Okay, let's edit that. Let's put show leak kinds equals all in there. Got an extra space, who cares? So then this one shows me basically who allocated it. Search.cpp line 128 allocated it, and then it went into vector stuff. Well, I want the highest line of code that's mine, search.cpp line 128. It tells you, it can't tell you who forgot to do the delete, but it tells you who did the new that goes with the delete that was forgotten. See, exit says program stop right now. Don't wait for destructors to run. See, so this is why, let's say, for example, one thing that people accidentally do with Project 1 is they say, oh, if there's no solution, I'll just print my error, my output of what was discovered and exit. No, you can't exit. You got to get back to main and let main do a return 0. If you do an exit, you stop destructors from running. Okay, other tools. Oh wait, we're past tools. So we're analyzing recursion here. Okay, so we've got this question. I've got a power function. We want to implement this function, so we want to calculate x to the nth power, where n is an unsigned integer. So x could be negative, but we're not going to produce the weird powers, like we're not going to do 2.3 to the 8.47 power or 0.23 power. So we're sticking to integer powers, and we're not doing like -2, we're not doing 1 over, etc. So we're not doing negative powers, we're not doing double powers. We just want to do simple things. So integers assigned or unsigned to an unsigned integer power. So if we write this, we can do two different solutions. We can have a very obvious solution with either n or n minus 1 multiplications, depending on whether, if I start with x, I would have n minus 1 multiplications. If I start with 1 and multiply by x n times, I'd have n multiplications, but either one is linear. So it's easy to write a linear solution. Less obvious is to write a log solution. And write those different solutions iteratively and recursively. So here's doing x iteratively. So I've got a simple base case because I was going to start out with x. So I've got a simple base case of, it's not recursive, but if n is 0, return 1. Otherwise, I set my result to x. I multiply, notice this loop runs n minus 1 times. I run the loop n minus 1 times, and I do the multiplication by x, and then I return the result when I'm done. If I had done it differently, if I had started out with 1 and run this starting at 0, then I could have gotten rid of that if. Because then I started out at 1, if n is 0, 0 less than 0 is false, the loop doesn't run, and we return the one we started with. So those are two different linear solutions. Now, what about if we wrote it recursively? If we write it recursively, we got to have a base case. So recursively, we've got to have a base case, and I wrote the shorter loop version here. Recursively, we've got the base case. If n is 0, return 1. Otherwise, return x times the power of x to the n minus 1. Now, if we do that, first question, is it tail recursive? All right, we call the function and then we return, but not quite. After the function is done, there's a pending multiplication left over. So this one's not tail recursive. It does have to do work after the recursive call is done. Now then, the next thing we could do is we're going to look at next time how to analyze this. So if we look at solving these, the first one, it's just big theta of n. There's just a loop that runs n times, pretty easy. This one, we're going to need another tool, and we're actually going to talk about that tomorrow. So we're going to mention it today, and then we're going to talk about how to do it tomorrow for some of these. So we could always write a recurrence relationship. In fact, we could write a recurrence relationship for the calculations for x. I say x to the nth is 1 when n is 0. Otherwise, it's x times x to the n minus 1 when n is greater than 0. So I could write a recurrence relationship for the calculation. I could write a recurrence relationship for the time. All right, so if I write a recurrence relationship for the time, it says the amount of time taken is constant 0 when n is 0, and it's constant 1 when n is greater than 0 plus. So it's not just constant 1, it's t of n minus 1. It's solve the smaller problem plus a constant amount of work. Now let's go back to the code. Let's identify C0 and C1. All right, so this right here, calling the power that with n minus 1, this right here, that's the t of n minus 1. That's the recursive call when n is greater than 0. When n is 0, where's the C0? Oh, C0 would be things like that. Lines 10 and 11 is C0. That's the base case. When n is 0, we have to check if n is 0, and we have to return something. So that's C0. Where does, I'm going to change colors here, where does C1 come from? So C1 comes from line 10. When n is greater than 0, we still have to do the if. Then other parts of C1 would be the actual subtraction itself is part of C1. So doing the n minus 1, doing the multiplication is C1, and doing the actual return is C1. So we've got a constant amount of work that we always have to do, and we've got the recursive work. So that's our recurrence relationship for the time. The time taken is the time to solve a smaller problem plus the amount of time I spent doing an if and a subtraction and a multiplication and a return statement. We could also write recurrence relationships for non-tail recursive amounts of memory. Usually the memory is pretty easy to see. We usually don't need a recurrence relationship for the memory. So we've got a recurrence relationship for the time. How do we solve it? Well, we're going to look at one way to solve it today. We're going to look at another way to solve it tomorrow. So the first way to solve it is substitution method. What we're going to do is we're going to write out t of n and in terms of t of n minus 1, etc. And we're going to substitute in for the recursive portion, and we're going to look for a pattern. Now, some of them can be solved with the master theorem. We're going to look at that tomorrow. The recursion tree method, I forgot. We got to get this out of here. We used to have a recommended textbook, and we don't recommend it anymore because it's kind of cryptic, but it's a really good resource. If you want a resource that you can keep for the rest of your life as a computer science person, it's called CLRS. Corman, Lyserson, Revest, and Stein is a book about algorithms. And if you get a physical copy, it's about yay thick. It's almost as thick as my hand. It's a book that you can keep and use forever, but it's a bit cryptic to read at some points. A lot of it is pretty cryptic to read at. So anyway, recursion tree method is another way to do it, which is in CLRS, which we used to talk about a little bit, but we forgot to remove from the slides when we got rid of CLRS. So let's stick to the substitution method today. All right, so here's our recurrence relationship and the code that goes with it. And so what we're going to do is we're going to solve this together. All right, so I'm going to write out my recurrence relationship minus the base case. We know it exists. It's up there. I need to solve the recursive part. So I've got t of n is equal to t of n minus 1 plus c1. Now, I'm going to write over to the right here, I'm going to write out this same recurrence relationship in terms of a different variable. Let's change colors. T of x is equal to t of x minus 1 plus c1. Okay, so back to the original equation. Over on the left, I've got the t of n minus 1 is on the right-hand side of the equals, and that doesn't help me much, okay? So let's write it out in terms of, let's substitute in. So what I'm going to do is I'm going to take n minus 1, and I'm going to substitute it in for x. I'm going to say, well, what if x was equal to n minus 1? Well, if x was equal to n minus 1, then what I would get over here would be t of, so if x is n minus 1, x minus 1 is the same as n minus 1 minus 1. So that's n minus 2. Or, well, let's just write that once there. Let's write it once as n minus 1 minus 1. Oh, wait, actually, I got a better idea. Let's put that original 1 in red. Hopefully you can see it. Black and red get a little close for me. Okay, so it's n minus 1 was the substitution, minus the original red 1, plus a black C1, plus a red C1. So we can simplify this to be, this is equal to t of n minus 2 plus the black C1 plus the original red C1. Well, I got it down from n minus 1 to n minus 2. Let's do that again. We got closer to 0. We got closer to a base case. So let's substitute in. Let's change colors. Let's substitute in for t of n minus 2. Well, t of n minus 2, if I set x equal to n minus 2, that's t of, so that's equal to t of n minus 3 plus a purple C1 plus a black C1 plus the original red C1. Now here's where we want to look for a trend and sort of skip ahead. So if I keep doing this enough times, I would get down to where I have this is equal to t of n minus, let's say, or let's just say t of 0. So eventually, if I keep doing that, I'll get down to t of 0, which is my base case. T of 0 plus C1 plus C1 plus C1. Okay, now the question is, how many times did it take us to get there, and how many of these do we have? So I started out with n minus something, right? To get down to 0, I basically had to do this n times, right? I had to do this n times, or let's say, let's do this another way. What if I said I could get down to, I'm trying different ways to see what makes best sense to you. What if I said I could get down to, I know I can eventually get to equal to t of n minus k plus C1 plus a bunch of C1s. Well, if I do that, then every time I did this, there was this extra C1. So there was k C1s, right? So if when I did this once, when I had n minus 1, when k was equal to 1, I had 1 C1. When k was equal to 2, when I had t of n minus 2, I had 2 C1s. Now when I have n minus k, I have k C1s. Well, what if I said, what if k happened to be equal to n? Then I would have, this would be equal to t of 0 plus C1 plus C1 plus C1. There would be n of these, which would be equal to, running out of room here, which would be equal to t of 0 plus n times C1, which would be equal to C1 times n plus, what's t of 0? C0. Aha! That looks like an equation that we're used to seeing. I've got a constant amount of work times n plus a constant amount of work. This looks like big theta of n. So I just had to do enough substitutions to see a pattern where I could get to the t of n minus k line, count up how many constants I had, and then generalize it. So we've said this thing is linear. Well, that's good because, we wrote two versions. We wrote a loop, we wrote a recursive version. It would be nice if the recursive version was also O of n time. Now, if you're having trouble with this, we're going to be doing another one soon, and also go back to the video, come to office hours. We'll be happy to go through them again. We're going to go through another one, get you more used to this. Okay, what if, I wrote over on the top of that. So it says, okay, the recurrence relationship is t of n equals t of n minus 1 plus c, and I got down to big theta. That was sort of the generic form of it. So I got big theta out of that. All right, what about if I had, here's a logarithmic implementation. At least I claim it is. We need to prove it. Claiming this is a log. So let's look at how I got from the code to the equation. So the code says I've got a result is equal to power of x to the n over 2 power. So I made a recursive call of size n over 2. And after that recursive call was done, I multiplied result times result. And if the result was, or if n was odd, I multiplied by x one more time for good measure. So let's say for instance, I say I want x to the 5th power. We would say, okay, well, is that a base case? No. Let's take x to the n over 2 power. So what I need is, I need x squared. Remember, integer division. So integer division, I need x squared. So we solve that recursively. That's our result. So we get result is equal to that. Let's assume it worked. That's how recursion works. We assume that the recursive call worked. When it was done, I took it and I multiplied it by itself. That gave me x to the 4th. So that was result times equals result. That was this line here, was multiplying it by itself. And then I said, oh, if n was odd to begin with, I've got to multiply by one more x in there. So line 5 says, Line 8 says multiply another x times that, and that gave me x to the 5th. So that's how this thing works. So if we assume that the recursive call works and does what it says, then we can do a recurrence relationship. So it says the amount of time to solve x to the 5th was equal to the amount of time equal to solving x squared plus some constant c1. So what went into c1? Well, basically everything but the recursive call. The division by 2, the multiplying result times result, the check if it's odd, the multiplying by x again if it was odd, returning the result, all that went into C1. C0 again is just the base case. Check if it's 0 and return 1 if it's a base case. So we've got a recurrence relationship. What we need to do is solve this slightly harder recurrence relationship. All right, so I'm going to get rid of that to make room because we're going to need all the room we can get here. So I've got T of n is equal to T of n over 2 plus C1. And then let's remember T of x is equal to T of x over 2 plus C1. All right, so I'm going to do my substitutions. I'm going to change colors earlier this time. Okay, so let's change to purple. So I want to substitute in for T of n over 2. Okay, so that would be equal to T of, well, if I take n over 2, remember, so nx is defined as n over 2, so I've got T of n over 2 over 2. So T of n, if I had, let's say I had 100, what's 100 divided by 2? Divided by 2 again is 25. This looks like n over 4. So T of n over 4 plus a purple C1 plus the original red C1. Okay, well, let's substitute in orange for the T of n over 4. Well, that's equal to T of n, or n over 4 over 2 is n over 8, plus an orange C1, plus a purple C1, plus the original red C1. Now, if I keep on doing this, I should eventually get down to, I should eventually be able to get down to T of, let's say, n divided by k. Okay, so I can get down to T of n divided by k plus C1 plus C1 plus a bunch of C1s. Now, we want to get down to the point where we've got T of 0, right? T of 0 is our base case. Now let's say, or no, not T of n divided by k. Sorry, I haven't done one of these in a while. Okay, not T of n divided by k. Because k changes each time. K goes from 2 to 4 to 8. So if I could get down to T of n over 2. Shoot now. I'm so used to just skipping to T of 0. I'm trying to do a different way to see if it makes more sense to you. But see, I'm used to skipping to T of 0. Let's do that because I'm having trouble seeing the right way to do it to do the explanation. Maybe it'll come to us after we get there. So if I get down to T of 0, it would take me some number of steps. It would take me some number of steps to get there, and I'd have some number of these, right? Well, how long is it going to take us to get to T of 0? Let's just do an example. Let's say I started out with 16. So I would have to divide 16 divided by 2, 4, 6, 8, 16. 16 divided by 16 would still be T of 1. I'd have to divide it one more time. I'd have to divide it by 32 to get to t of 0, right? Because if I start out with n with 16, to get to t of 0, I've got to divide by 32. So I had to divide by 2, 4, 6, 8, 16, and 32. So I had to divide basically 6 times. What if it was a million? A million, I'd have to go 500,000, 250,000, 125,000, 62,000, 31,000, 16,000, 8,000, 4,000, 2,000, 1,000. That took me about 10 times, right? It took me 10 times to get from a million down to 1,000. Then I go to 500, 250, 125. It's going to take me another 10 times to get down to 0. It took me about 20 times. So it's going to take us about log n times to get here. See, if I got down to, let's say I went down to t of n. Let's say I got to t of n divided by n, right? I could eventually get to t of n divided by n plus a bunch of c1s. And if I divide once more, I could get to t of 0, right? So if I can get to t of n divided by n, that's t of 1. If I divide by 2, that's t of 0, plus a bunch of c1s, plus c1, plus c1. There would be basically one more c1 than we had last time. Okay, so I need to divide by n. So I need to divide by n. Well, how do I get to n? What is n equal to here? Well, n's equal to n. But what if, how many times, what we want is how many times did this take? What is k here? Well, what if, let's just assume, what if n was originally equal to 2 to the kth power? 2 to some power of 2 to some power. Like if n was equal to 2 to the 4th, n would be 16. If n was 16, I could get down to 16 divided by 16 by dividing 4 times. I'd have to divide one more time to get to t of 0. So in k times I can, so what is k then? I still don't know what k is, but I know that it's related to 2 to the k is n. Well, if 2 to the k is n, then this must mean that I take the log of both sides. Log base 2 of n is equal to k. So I had to do this about log n times. Really, it's log n plus 1. And that's only if it's exactly a power of 2. If it's not exactly a power of 2, it might be the ceiling of log over log of n. It might be the floor of log n, something like that. But I think it would be ceiling. Yeah, ceiling of log n plus 1 is how many times we had to do it. So if we did it log n times, we could get down to t of 1. Do it once more, we can get down to t of 0. So k here is basically equal to log of n. And so that's our, and again, I wrote over the top of it again, that's our, we get big theta of n out of this because that's how many times we had to divide by 2 to get down to a base case. And is it log of n? Is it ceiling of log of n? Is it 1 plus ceiling of log of n? It's still big theta of n. So that's our recurrence relationship. So we take that recurrence relationship, we solve it, we get big theta of log n, and now this fits the power. It also fits binary search. If we wrote out a recurrence relationship for binary search, we get the same basic equation. T of n is equal to t of n over 2 plus a constant amount of work when it's not a base case. So anytime we see this recurrence relationship, we can now skip ahead and say, oh, I know this one is big theta of log n. I've already solved it. Now we're going to look next time when there's division going on, an easier way to solve this. Okay, So, for example, what if we've got a recurrence relationship that cuts a problem into two parts, but both subproblems have to be recursively processed? Well, this was cut it into two halves and only solve one of them. This would be something like T of n is equal to T of n over 2 plus T of n over 2 plus some other amount of work. So that would be equal to 2T of n over 2. What if it cuts it into 3 parts and processes 1 or 2 or 3? What if the non-constant work, what if the work after the loop was not constant? What if this was like n over here? So then we'd have to do all of these by hand. There's a better way, though, is what next time we're going to learn the master theorem for solving these. Because as we get to seeing, like we can say, hey, let's look at, oops, I forgot this was an animated slide. So there's processing 1 or 2 or 3 pieces. What if there was additional non-constant work after the recursion was done? So when we do this, we could write all these different equations down and solve each of them one at a time using substitution, but the master theorem will give us an easier way to do it in many cases. Not every case, but a large number of them. Okay, here's another example of one that is, hey, I could write this out really easily recursively. So this is the binomial coefficient, or if you've taken a statistics class, this is n choose k. Like, hey, I've got 10 different colored pens that I can use and I need 5 of them. How many ways are there to choose 5 different colored pens out of 10 possible different colors? So this is n choose k, and there's a simple way to write it in terms of factorial. So like 10 choose 5 is equal to 10 factorial over 5 factorial, 5 factorial. And we could write this out recursively in terms of factorials. We could write factorial recursively. We can write n choose k. There's a recursive definition for that that we'll look at later on. And some things like this, it turns out, are painful to do recursively, and we're going to get to very complex, very large complexity. This one's actually going to turn out to be exponential. So we'll look at this one in a future lecture also. Now we're just about done for today. One thing I wanted to mention, interesting thing that happened to me over the weekend. So actually on Friday I went to get some takeout food from a local restaurant here in Ann Arbor, and while I was waiting for it to be brought up, 2 people came in waiting for their order, and they're talking about coding. So of course I had to step into that and find out where they worked. So they worked at Honda Research right around the corner from the restaurant, and they're talking about coding and talking about algorithms. And I said, oh, that's what I teach at U of M. And they said, oh, we're both in robotics. We go to get a job interview for robotics. What did they ask us? Data structures and algorithms. I said, that's what I teach at U of M. They said, I can't believe one of them said, I've got a master's degree in robotics. I go to a job interview, they ask me data structures and algorithms. All the time, that's what they want to ask. So, it's really, this class is really important when it comes to interview time, internships, long-term job interviews. This stuff is going to come up. And so 281 is, as we said, it's a lot of work. You put a lot of work into it, you'll get a lot out of it. But it is really the #1 class that interviewers ask about. Why? Not because it's 281, because the things that we cover are what make you a useful hire. Like before 281, maybe they could have you do some little web stuff or maybe some trial stuff, and maybe it's really just to get a feel for what can you do. Are you a good employee? But after 281, they can put you on real projects. One of my IAs, previous IAs, who's graduated now, got a summer internship at Microsoft. And she was just looking around at all the people that were working there, And she asked the supervisor of the internships program, it seems like everyone I know here from U of M is just better prepared than anyone else. Like Stanford, MIT, Berkeley, they're just not as prepared for this job as we are. And the director of the internships program told her, U of M students get a higher percentage of return offers than any other school. Now, granted, this is one person at one company, but that's the takeaway. That's what we're preparing you for. And that's IA, granted, she's one of my IAs. She's not your average student. They gave her a 12-week project. She finished in 4 weeks. She said, what else can I do? Well, they said, well, we didn't quite get everyone we expected. Here's another 4-week project that there's no person for. Here's another 12-week project there's no person for. She did that in 4 weeks. She said, what do you got? I still need things to do for my last 4 weeks. Her boss said, I'm sending you to the Cortana group. They'll give you something. So that was her summer internship, ended in like middle of August. She came back to U of M. In like January, she got an email from someone there in the Cortana group saying, hey, your changes are going live in like another 3 weeks. Stuff you did is going live to Microsoft Cortana. So, we really do get you ready for the real world out there. So someone said that's a Michigan difference. And that's 281. So we do ask a lot out of you. We put a lot of effort into planning good projects that give you those tools you need to make those contributions. All right, I'm going to end here a few minutes early. I'm going to get some lunch, and I'll see you in Profis hours in like 43 minutes-ish.